So there's one other thing that I wanted to talk about that the book doesn't bring up, but it ties it back to probability, and it's so darn cool. I just could not resist. So suppose we let omega be some domain, so some nice bounded domain. And we're going to let xt be the location of a random walker at time t. So you can think of this as some little particle that's diffusing about under, following the heat equation, just kind of like randomly, blundering about in the domain, something like that. So the particle x is at location xt at time t. Okay. And so he's somewhere in omega. Okay. And let's prescribe a boundary condition. So let f be a function on the boundary of omega. And let's take tau, let's let tau be the hitting time of the boundary. And so the meaning of this is the first time that the random walker reaches our boundary. So this is the first time such that xt is in the boundary at that time. So this is the hitting time of the boundary. Some books or treatments would put like a little subscript for hitting time on the tau, but it'll be clear from context what we're doing right here. So now if you've got like say a Brownian motion type random walk and your region is bounded, then the probability is 1 that it's eventually going to hit the boundary. So so this thing is well defined, and so you should think of like some kind of, all right, here's your here's your omega, and so we've got some point in here. Say we've got a point like z, and then we let our little random walker, and he just sort of like diffuses around, and who knows what he does. He just like wanders randomly, right? And so after some length of time t, his location is xt, right? So xt is actually a function that takes values in omega and it's indexed by time, but whatever. That's more technicality than we need. So if you have some region of the boundary, so some subset of the boundary here. So let's take like this region here. Okay, let's call this A. We're going to let pz of A, so this is going to be a measure on A, a probability measure, and it's going to be the probability that the first place that we hit the boundary is in A. So remember, tau is the hitting time of the boundary. So x tau is location of the escape, or first time you hit the boundary, right? So the probability that you breach the boundary through the set A, given that your initial location was z, okay? So this is the probability that if you start at z, you'll leave the set through A. So these are conditional probabilities because we're conditioning on the fact that you started at z. So this family, so z can be any point here in omega. This is a family of probability measures, and like I said, they are conditional probabilities. And they give you probabilities of the they tell you what the probability is of a set in the boundary. So and they are called hitting distributions. Or escape measures. Okay, so those are the hitting distributions on the boundary. And so we could talk about this in a totally discrete context too. So perhaps you have some like network, a grid of some kind, or some other kind of network, whatever, it doesn't matter what the geometry is. That's probably big enough. Something like this, right? And then we're going to prescribe the values of a function on the boundary. So maybe we'll say, so here's f, and f is maybe this vertex has 1 and 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 1. And then we have a bunch of zeros. I should have drawn a smaller network. Okay. Something like this, right? Okay, so we've prescribed the value of the function all the way around whatever vertices we've defined to be the boundary of our setup here. And now let's take a look at what's going on here. So if we look at x sub tau, that's the location where we first hit the boundary. Once we hit the boundary, the value of the function is defined on the boundary. That's where it's given, right? So we're allowed to talk about f of x at that point. Okay, so what is the value where you first hit? Well, it's going to be a random occurrence where you first hit, so you can't actually say what the actual value is, but you can say what the average value is, or what the expected value is for where you hit the boundary. Given that you start at a point z, so I'll put a little subscript z right here. And so the way that this expected value is computed is you take the sum over, like, what is the value at the point x in the boundary, and what is the probability that we hit the point x given that we start at z, right? And so then so let's go back over here to the network, and I'll draw some pictures, right? So like if I'm if I started this z right here, then probably the expected value is going to be pretty close to 1, because there's a very high probability that I hit 1 on my first random step out of the gate. And even if I don't hit 1 immediately, there's a good chance that I hit it pretty soon after that by doing some other choice, right? Whereas if I start off at some point over here, then I'm probably going to have some z value that's very close to 0, because I'm surrounded by zeros on so many sides. And so in general, what I'm going to do is I'm going to say, let's start at some point and let's do a random walk. So maybe I go bink, 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 bink. Okay, and so then I did some little random trajectory, and then that's where I first hit the boundary, and so my value there is 0. So part of this summation right here is going to have a 0, and it'll be associated to the probability of whatever this particular walk was that I went through there. So if I start from this point, how likely is it that I exit through right there? That's the meaning of this probability right here. So this extends to the continuous picture. So you can talk about, okay, how likely is it if that guy keeps, diffusing around for a while, that when he does finally leave, he goes out through a point in A. All right. So in the continuous case, then, when we add these up, we have to integrate. And then we are integrating this probability measure. So now its argument is pz dx, because it's a measure. We're doing something continuously distributed. But in fact, this is the integral over the boundary of fx p z comma x dx, the Poisson kernel for the set that we're looking at. And so the probability measure in the continuous case, the probability that we leave through A, that we escape through A, that's going to be the integral just restricted to A of p zx dx. Yeah, and so just to get a picture of what that looks like in the continuous case, here's a little picture that I drew from what we saw before, and you can see that, so in this blue region that I've got here, this would be A. Let's label it actually. So this set across the bottom here is my A. And then the probability that I leave through A, given that I started at Z, well, look at the green curve, right? So the area of this region is the probability that I leave through A. And then, as you saw on the previous clip, if Z gets closer and closer to the boundary, then this distribution converges to a point mass, because the probability that I leave through this point, given that I start at this point, well, the probability is 1. And that's exactly what that discrete probability is.